My name is Sanghamitra Neogi. I'm an assistant professor at the SMID Aerospace Engineering Department at the University of Colorado Boulder. The name of my lab is Quantum Lab, and the full form is CU Nanoscale Transport Modeling Laboratory. What we do in the lab is we computationally design materials, specifically the transport phenomena in the materials. Transport means transport of information or energy, which is happening at the very, very small scale, the nanoscale. We are working on designing new materials which can bring in changes to our existing technologies or bring in future technologies in our lifetime, which is kind of what we are doing right now. You can see the effect of it. For aerospace applications, one of the really newer push is coming in the direction of hypersonics. One of the challenges are how to maintain the tip, the leading edge of that, because when these vehicles are going through atmosphere at a very, very high speed, these tips get extremely hot. And one of the materials we are looking at is called this category of materials called high entropy materials, which is, the name is pretty fancy. What it means is that there are lots of kind of configurational degrees of freedom, and that is possible because these materials have lots of different elements in them. Lots of metal and combined with oxygen, carbon, and nitrogen. The uniqueness of my lab is that it sits between physics and engineering. We are kind of understanding the physics principles that could be applied for various engineering applications. But what is absolutely crucial to have is strong math background, because without that, one cannot understand the good algorithms, how to learn from them, how to advance them, how to update or write your own computational code, because this is entirely computational research. The kind of projects we are working on is very interdisciplinary, and it can find applications in multiple disciplines. The application of machine learning techniques for material science has gone through kind of a big revolution. What we are doing is we are using this to predict the properties of devices. What could happen once this material's in an environment which it has not seen previously. And this journey is possible only because of how we are using the machine learning techniques. I maintain a regular group meeting. In that meeting, everybody presents their work, but this is very informal. And there are multiple purposes. Of course, this is training you to talk about your research. The other thing is you get to learn about other projects going on in the group, which again, from the same versatility point of view, that this gives you ideas about other things going on. The other thing is the universality of these physics principles, that we are looking at radiation-hard electronics, materials for hypersonics, quantum applications, or thermal challenges in these RF devices. But many of these are connected through these universal physics principles. Identifying them, leveraging them, and designing them or harnessing them, that's pretty cool, because then you know how things work, essentially, from the very core. So understanding that and applying and bringing that up to the engineering community is pretty new, and that's very exciting to us.